Okay, so this is what was an in-class assignment on winding numbers and zeros plus poles. And so I'm going to write this up as sort of a lecture thing. So what we've got is gamma is a curve, positively oriented path, and that's supposed to be a closed path. And f of z is a function that's analytic on and inside gamma, except for a finite number of poles, right? So there might be some discontinuities, basically where you're dividing by 0. And we assume that f of gamma of t does not equal 0 for all t in a comma b. So we have this path like this, closed path, and simple. It doesn't intersect itself. There's some poles inside. There might also be some zeros inside, but there's no zeros on the path. And we want to flag down some consequences about this. So first off, if we do this substitution, what do we get? Gamma prime of t we know is, dz equals gamma prime of t. And so we get integral around gamma of f prime of z over f of z dz equals integral from a to b f prime of gamma of t times gamma prime of t dt, because that's our, so I forgot the dt there, dz, that's our dt, over f of gamma of t. And so that's our integral that we get. Nothing hugely fancy there. Okay, so derivative of f of gamma of t using the chain rule is that, right? Because derivative of the outside times derivative of the inside. And that's this part of the integral. So integral of ground gamma of f prime of z over f of z dz equals, in fact, the integral from a to b of, now I'm going to get a little bit messy because there's going to have to be lots of fractions. F of gamma of t, that's my denominator. And now my numerator by this last calculation is the derivative of f of gamma of t dt. So now if we assume f of gamma of t is actually r of t e to the I theta of t, and note r of t is never 0 because we assume that f on the path is always, there's no zeros of f on the path. So what's the product rule of f of gamma of t? So d by dt of r of t e to the I theta of t is r prime of t e to the I theta of t plus r of t I theta prime of t e to the I theta of t. And note that our path, whatever it is, whatever f of gamma of t is, it's some kind of path. It's a collection of points in the plane, and we can always write points in polar coordinates, so that's why we can write it like that. And that gives us this thing for the derivative. So what we're getting there now, if we look back up at this, is that we have integral around gamma of f prime of z over f of z dz is integral from a to b of the derivative of f of gamma of t, which we've calculated to be this thing. That's an I, theta prime of t, e to the I theta of t. And f of gamma of t is stated to be this. So that's r of t, e to the I theta of t, dt. And so we can break this into a couple of different integrals because if we break it into two fractions, the e to the I theta t will cancel out of 1, and we'll get this. And then I can cancel out an r of t and an e to the I theta of t out of these two, and we get I theta prime of t quantity dt. So we end up with two integrals, a, b, r prime of t over r of t dt plus I integral from a to b theta prime of t dt. That's an I out front. Great, so why is the integral involving r of t equal to 0? And so the integral involving r of t is the integral from a to b of r prime of t over r of t dt. We know that this is never, r of t is never 0. So we can integrate this thing. We get log of, oh, and these are real functions. But we had a closed path. So that means r at the end and r at the beginning are both the same. So it gives me 0. Okay. So, oh, and also r of t is strictly greater than 0 because it's the distance from the origin. Right, so all these integrals are nicely defined. So what we have here is I, so at the end of the road, and before we get to this, integral around gamma f prime over f equals I integral around a to the b theta prime of t dt. And this is something involving the winding number, is this integral. So we'll talk a little bit about what that means. So what we have here is we have a path in the plane, gamma of t, and then we have a function f. And the function f takes our path gamma of t to another path, like that. That goes and wanders around the path. So this is f of gamma of t. And f of gamma of t, and this is gamma of a equals gamma of b, that's our start point. And we'll say that that's my start point, although of course I shouldn't start and end the point somewhere in between, inside the picture, because there's no space to write out what that is, but we'll just leave that as the start and ending. So f of gamma of t we rewrote as being r of t e to the I theta of t. So at any point on this curve, you have a theta of t and you've got an r of t. So what's the integral from a to b of theta prime of t dt? And this is just going back to what's the meaning of the derivative. And so the derivative is a rate of change. This is the rate of change of theta with respect to the parameter t. So when you integrate it, what do you get? You get the total change in theta, right? And theta is measuring your angle from the origin. So if you go around the origin once, right, you get 2 pi because you've gone around, the total change is 2 pi. And if you go around the origin a second time, then your total change is going to be 4 pi. So what this integral represents it's 2 pi times the number of times f of gamma of t wraps around the origin. But of course, we do have to be a little bit careful about this, especially about this phrase, because again, it measures the total change. And so if I have a path, instead of like this, if I have a path that goes around the origin once, right? And so there's a change of 2 pi, and then it decides to go back, right? Here, say my path is this. Counterclockwise, your path is a positive, and one's clockwise. And clockwise is a negative. So the total change for this one equals 0, because you could have closed these up a little bit so they covered, so you actually sort of went around. But if you go around once this way, and then you unwrap by going around the other way. So total number of times you go around the origin, right? Count everything in one direction as positive, and everything in the counterclockwise direction is a positive going around the origin. Everything around the negative is a negative. And this thing is called the winding number. So 2 pi times the winding number, that's the integral of theta prime dt, and keep in mind that there's an I floating around here, so it's 2 pi I times the winding number. So that's a calculation for this integral, connecting it to this thing called the winding number of the image of the path. So can we calculate this integral in a different way? Well, yes, we have residues now. So suppose f of z is a zero multiplicity m at z0, so f of z would be this, g of z is analytic, and g of z0 is not equal to 0. So what is f prime over f? Well, f prime is, using the product rule, that. So it's differentiate the z minus z naught to the m, and then differentiate the g of z. So f prime of z over f of z is, and I'll put the m out front where it usually is. I forgot it and to add it up later than the last time. G of z plus z minus z naught to the m g prime of z all over f. Or where's my f? Z minus z naught to the m. And if we simplify this, what do we get? Well, again, we're going to break this into two functions. We get two fractions. We get m over z minus z naught That's this first term divided by that, by the denominator, and then g prime of z, g of z. But g of z0 is not 0, so this is analytic at z0. In particular, it does not have a pole or a singularity or anything, so this thing you could write out as a Taylor series. So what's the Lorentz series for f prime of z over f of z? The Lorentz series is going to be f prime of z over f of z equals m over z minus z naught, plus the Taylor series for this thing, which is a0 plus a1 z minus z naught, plus dot, dot, dot. So the residue of, and this should be the residue of f prime over f. The residue of f prime over f at z0 is m. It's the order, it's the multiplicity of the 0 of f of z. Okay, so that's a nice thing. What about if you have a pole? Well, exactly the same argument goes through, right? So again, and we're looking actually for the residue of f prime over f. So f of z equals g of z, z minus z naught to the minus m. What's f prime of z? Minus m, z minus z naught to the minus m minus 1 times g of z plus g prime of z, z minus z naught to the minus m. So f prime of z over f of z is what? Well, we have this long derivative, minus m, z minus z naught to minus m minus 1 times g of z plus g prime of z, z minus z naught to the minus m, all over g of z, z minus z naught to the minus m. We do our calculations. We end up with minus m over z minus z naught. Because when I look at this term, the g's cancel out. I have minus m, the z minus z naught to the minus m cancels out, which means I have a z minus z naught to the minus 1, which puts it down to the denominator, and then plus g prime over g. And for the same reason, right, g of z has a Taylor series. That means that this is the pole. And so a residue here is the order of the pole. So what we've done then is we've created a function. This function f prime of f has got a simple pole everywhere the original function f has either a 0 or a pole, and the residues for f prime over f are exactly the orders of the poles or the multiplicity of the zeros. So we set z to be the number of zeros counted by multiplicity inside of gamma, p the number of poles counted by order. So if we actually evaluate f prime of z, if we evaluate this integral, what is it? It's 2 pi I times the sum of the residues of f prime over f inside gamma. But if z is the number of zeros counted by multiplicity inside of gamma, and p is the number of poles, we get this result. So this integral now, we found a second way to think about it in terms of zeros and poles. So putting it together, right, we know that the integral gamma of f prime of z, f of z dz can be rewritten as 2 pi I times the winding number. Equals 2 pi I times z minus p. And so is there a way to think about this? Try and see if I can move my, sometimes this tablet is kind of a pain. I'll do this. I just need some more space to write some stuff. So we'll just push all that down to the bottom. We'll say, okay, so putting our two results together, we get winding number is z minus p. So why should these two things be connected? This is kind of an odd thing, right? We're saying, I take a function, right? I have a function, and I have, say, a 0 here, and a 0 here, and a pole here. It makes them all simple poles. And I've got a path, gamma, that goes around it like this. And I have a function f. So 2 zeros minus 1 pole equals 1. So my winding number should be 1. So what I'm doing here is I'm assuming multiplicity and the order of the zeros and the poles equals 1, just to simplify this example. So the winding number should be 1. So what does this actually mean? Well, if we think about gamma in terms of f, if we think about gamma now as being broken down into, start here and we'll go around to the first 0, and suppose instead we go in and we do a little wrap around it, and then we come back out, and then we go back in, and we do a little wrap around it, and we come back out, we go back in, we go to the pole, and we do a little wrap around that, and we come back in, and we end up back there. And that's a path that's sort of the same thing as gamma. It does what gamma does, except instead of having gamma sort of far away from the zeros and the poles, it becomes very close to it. So what is this going to look like? What does a little circle around z go to? So z here is a 0, so this little circle is going to get mapped to a little circle around the origin. This little circle will also get mapped to a little, well, it doesn't have to be a circle around the origin. And those will both go this way. Here, near the pole P, F has a pole, so F is sort of 1 over z to the n, right? And what we know about 1 over z is that it flips the orientation. If I'm going this way, the image of the path is going to be oriented in the other direction. It's going to be going, this is going counterclockwise, so the image is going to go clockwise. We also know poles get mapped out to infinity. So this is going to get mapped out to this little circle here, would get mapped out to a big circle that's going clockwise. So we can think of the path, since it goes around, the path gamma, since it goes around 2 zeros and 1 pole, the path gamma, whatever it's going to do, it's going to end up going around a 0 once, then around the other 0, and then it's going to go out and go around infinity once, with infinity on the left-hand side, and then it'll come back to wherever it started. So what does that mean? Well, your winding number is going to be 2, right? You go around the origin twice, once for each 0, and you go around infinity once, and going around infinity is in the opposite direction, and so that gives us a connection between the winding number and the number of zeros and poles. And so, for example, if we have, say, this function, right, which has got a 0 of order 1 here, and a 0 of order 1 here, and a pole of order 1 here. And if we take some path that goes around that 3, what we'll know about this path is that it will go around the origin once. Don't know what it'll look like. Right? It might not necessarily do this whole thing that, you know, going around the origin twice and then back around the pole, but we know it'll go around the origin just once. And so that connects the winding number to the zeros and poles. If you can figure out what winding numbers are, right, take advantage of the structure of F to take paths in the domain and then map them to paths in the range where you can think about what that path looks like, then you can start counting where zeros and poles are. Now figure out how to end this.